So actually the first thing is, you know, I had a small discrepancy in my code that was causing the differences between the relationship matrices that a.map makes and the manual one I was showing you. So I have a fix up here is these two lines of code. I think one important thing to notice is the one I had before would have made equivalent predictions. It's just really a matter of it's a matter of the scaling and what the values look like. So this will give you the comfort that they're going to be the same. And so now you have values that are more, these should be equivalent to 1 plus the inbreeding coefficient. You can also think about it as being related to just the number of homozygous loci that an individual has, right? So that's why it's related to inbreeding. That's about all I really wanted to say about that. So if everybody is caught up, we should have a kinship matrix. Oh, I'm sorry. So you could also, since I'm just saving this over my file on Google Drive, you guys, any change or addition that I make, it's going to be on there, so you guys will be able to download that fresh. So I'm just going to give you guys a second to get that all down.
I also just put up on the board a reference on the right there. Interpreting these coefficients we've made is not a real issue. There's a lot of confusion in the literature, and you know, that paper I wrote to try and get one possible interpretation of what that inbreeding coefficient means for an identity type data.
Probably put that paper in the Google Drive, actually. Maybe next break or something. Yeah.
In your code, when you're doing the model matrices function, is there any reason why you're assigning equals instead of assigning something?
Where's that?
Like we equals on matrices. It's a good thing like less than.
So those actually are equivalent assignment operators in R. It's actually generally considered a no-no or a faux pas to use this equals. I'm not strongly opinionated. I do tend to try to avoid this equals, but then occasionally, apparently, I use it anyway. So these have the same effect. That's a great question. So if you want to be grammatically correct in R, then use this. And I think it has to do with you don't want there to be too much confusion between the equals are going to show up in inside the functions to indicate options and things like that. So thanks for catching me on that. Does everybody have these two lines copied down? We're about all caught up? Cool. Okay. So that means that we should all have a kinship matrix. You can look at the dimensions of that matrix if you're interested. just to be sure you see, is 326 by 326. That is the size of our training population. So this relationship matrix contains only training individuals. In other words, we're going to, in just a few minutes, get to the part where we're predicting unphenotyped individuals, the 82 individuals we put into the test set. But we're not there yet. So now we're going to use gblup in two different functions. First, the mixsolve function we already used. So firstly, just to be clean about it, so we're making a new model matrix. This is just to make, probably didn't need to do this, but I'm just want to make sure that everything is correct, correctly related. What this is doing is saying that in our data set, the phenotype, the training data set, we want to relate the phenotypic observations to the clone. And then, so we want that to be related to the relationship matrix. So I put the levels equal to row names of K here is a trick that's going to be important later to make sure that even when you have unphenotyped individuals in your relationship matrix, that you get columns for those individuals. So just consider this a trick and something that you should keep in there to make sure that this model matrix correctly relates the phenotypic observations to this relationship matrix, because that's what we're going to use to make our prediction, okay? So if we make that, and actually probably helps just to show the dimensions of the Z matrix. So it's 1,662 phenotypic observations, 326 individuals on the columns, right? If this had been a marker matrix, that would have been 1,000 columns, right? So now we can run mixsolve again. So notice a slight difference from the previous mixsolve that we ran. So this time we have a different Z matrix, right? Now it just relates observations to the relationship matrix instead of containing the markers. So before this was a marker matrix. And we include this new option K, which just happens to be equal to K. That is the relationship matrix. So mixsolve knows that this means this is the covariance matrix to use when calculating the BLUPs for the random term. So you can run that. And then we can look at what's in that. Okay, so I don't know how long it takes to run on everybody's computers, but so there's a couple of important things. So you can notice V sub U is something that you get in both. In the previous one, this was in the mixsolve for ridge regression, this was equivalent to the marker, the variance in marker effects. And then I had that little equation. In fact, I can go back up here and run it to show you this equation here. If I run it, I get 0.7579, and so there's a little bit of rounding difference. But you can notice that I don't have to do that equation. I get 0.758. It's basically the same thing. And I get the same error variance when I compare mixsolve doing ridge regression versus gblup. So now this is equivalent to the additive genetic variance that is explained by the kinship matrix. Okay? And so again, we can use this to get a sort of estimate of heritability. I think if you calculate it, it's around 0.45 for this trait. So that's actually all there is to it. I guess we'll get into this a little more, but now you have U. I suppose I could do something like put a histogram of U. So U, when you look at the ridge regression output, is 1,000 long because the marker effects, they are the BLUPs for the markers. But now U are the BLUPs for the individuals, which corresponds to the genome estimated breeding value. So you can look at that if you'd like. So I just made a histogram of the BLUPs. Notice that they're centered on 0, just kind of corresponding to the average breeding value in the population. One thing to note is that the BLUPs are in the original units of the trait. So this CBSD trait that we've scored, the disease severity score is on a scale of 1 to 5. Not exactly your ideal distribution of a trait. It's, actually ordinal 1 through 5 scores. But anyways, this is just the 1 through 5 score centered on 0. So you can interpret differences in the BLUP just as you would interpret differences in your original trait, which is really handy, especially for a breeder or somebody who knows their crop deeply. The next thing I want to show is just another function in our BLUP package. So kin BLUP works a little differently. I think it's a little more user-friendly. So I know I showed you the sort of harder one first, but my hope is that by understanding Mixolve, you get a deeper understanding of what's going on. The kin BLUP function only does gblup, so you can't do ridge regression in it, but you can do the same thing. In fact, what kin BLUP is doing is using Mixolve just with a nicer user interface. So there's a couple things we do have to do differently here. So for one of the things I'm going to do now with this next few line of code is we're actually going to have a relationship matrix. I think, let me make sure that's actually what I'm doing here. So I'm actually going to make a relationship matrix with all of the markers. All of the individuals, training and test. Yes?
I'm getting the different values for that.
For this? That you got a different value than this?
Yes.
How different?
I get 4.77.
That's
you get
interesting.
4.77 if you use that old calculation of K.
Really? Okay. That's fun. So that's probably, so apparently recalculate your relationship matrix, either using AMAT or using the new formula that I provided, and then I guess you should get the correct variance. That's fun. Okay, so a few things to know about kin BLUP, and all of this I'm kind of just verbally communicating what you'll see in the instructions to use it. So we're going to make a prediction of unphenotyped individuals now. Otherwise, this would be a little bit more similar. So the first thing is, in our phenotype data set, we need observations for all of the phenotyped individuals. We're just going to have missing values. We're going to set missing the observations that correspond to the training data set. So I have these two, first 3 lines of code are going to make this, or kind of getting this prepared to do kin BLUP. Okay, so I make a copy of the phenotype data set here. And this is the entire phenotype data set. I just don't want to model it. So we have training and test individuals. Then I have, I'm selecting just the rows of this data set that correspond to individuals in the test set. And then I'm setting their phenotypic observations to missing. I'm hiding their phenotypes so that we can make a prediction for them as if they were unobserved. Okay? And then I'm doing an additional little trick to accomplish the nesting. So we had rep nested in location. So the thing that does generally make kin BLUP easier is it takes a data frame, which is this phenos 2 that we've made. So we tell it, look in this data set. We tell it that geno, so this is the variable in the data set that corresponds to the individual ID. We tell it that this is the variable in the data set that corresponds to the trait that we want to map. We then tell it the following things. So we tell it K is equal to, now I'm making a relationship matrix actually within the function. You could do this separately, so you could make a new K, but I'm using the entire SNP data set because we want all individuals. So notice I'm not making any model matrix statements. That's the nice thing here. I'm not making my incidence matrix. It's going to do it for me. But what I had to do, so then I have a statement fixed. I can also have a statement, I think it's covar, if I had any continuous covariates like temperature or planting date or something. I don't here. So I have a location effect, and this, what I've done here is made a variable that is the combination of location and rep. And that's the equivalent. What it's going to do is make a model matrix behind the scenes that's equivalent to the one we did. So if you don't have a complex model with nesting and stuff like that, then you could just have location and, I don't know, year or something like that. So you specify the fixed effects, and with any luck, this should give you the identical results. So I ran this. Yeah. So notice that I get the same, out of this I get the same genetic variance explained and error variance because we have the same phenotypes in the data set. We just have new genotypes, and since the test individuals don't contribute to the model estimation, they don't contribute to the actual variance explained. A new difference is our BLUPs are contained in the object G here, and they are 411 long. So we have a prediction for every individual whether or not they've been phenotyped that comes out of this. We can do a few things. We can look at their values just to, oops, just adding some things as I go. So again, you can look at the distribution of the BLUPs just to kind of see that they are on values that make sense relative to the trait. But what I'm really ultimately trying to want to get at here before we do any, say, tests of prediction accuracy is one of the things that next is I want to prove that the ridge regression and the GBLUP give the same values. So we've now made model outputs for ridge regression and GBLUP. So the first thing we have to do, this line of code here, is going to, so ridge regression estimates marker effects. That doesn't actually give us a prediction yet for the genetic value of an individual. GBLUP goes straight to the BLUP for the individual, the breeding value. So what this is doing is multiplying the marker relationship matrix in the training set. So we're not making predictions in this case on unphenotyped individuals. So I'm actually going back to the original ridge regression, and I'm multiplying that by the marker effects, which were contained in this U. So if I do that, I get a vector 326 long that contains these breeding values. I make another vector that contains the next line. Just kind of extracts the BLUPs from the GBLUP model we did in Mixsolve, and then we can make a plot of the relationship between them, and they give you, oops, the same answer. So let me know if anybody doesn't get that answer. Does everything make sense? Everything's good?
Not fully formed.
Yeah, we can't exactly say.
Okay.
Fully
Okay.
form it.
Okay. The key trick is, I think part of it is that everything is done under the assumption of this normal distribution, and just in one we use covariance. Yeah, actually, I could use better words to explain why. I mean, there are a few papers that it was kind of like a realization someone had, like, oh, these turn out to be the same thing.
So they are different?
Well, in the sense that they make the same, they have the same answers as long as you you treat your markers that go in as predictors the same as, and then you create the relationship matrix in the right way. If you start using different relationship matrices, for example, they wouldn't be the same. Like if you did, there's some different formulations for the relationship matrix, or if you didn't scale one and you scaled the other, for example, you get different answers. They have some, for example, one advantage of if you're not going to update your training population, you have marker effects. You can just store those, and then anytime you get new genotypes, you can just multiply them by the marker effects and you get an answer. With GBLUP, you have to make a new relationship matrix that incorporates the new individuals from scratch, and that can be a pain in the butt when you got, thousands of individuals, because it takes time when you have lots of markers. Or if you have millions of markers or something crazy, doing the ridge regression would take a long time. So there are some, I generally use GBLUP. So I think we're all on the same page, so let's take the next step. So everybody's ready. So the thing we haven't gotten into yet is prediction accuracy. So let's make some predictions of the test set, and then from there on we can start to calculate. We can start to compare some of the other models. But first I want to point out that there are different ways that you can deal with calculating prediction accuracy that I wouldn't say that there is a correct answer to this. People deal with it differently in the literature, especially if you look at animal breeding literature, because they have some different kind of phenotypes, because, for example, they're dealing with like the outcome of progeny testing. Anyways, those are things that we shouldn't be worried about here, I think. So there's two ways that I'm going to show to correlate. So we make a prediction. We get a single value for each genetic individual. But in our phenotype data set, we have replications for that individual. So kind of the obvious way to calculate the accuracy on the test set is to correlate the raw phenotypes on the test set with the predictions for each of those individuals. So that's one way. The other is to reduce those replications on the test set down to a single value on each individual. That's kind of a two-step process, and this is actually kind of the way I usually do it myself. So we're going to calculate, and this is going to show you another R package that does mixed models, but not for prediction. It's just for solving linear models, no covariance matrix, no markers. But it's a handy one that you may need at various times. So we're going to calculate what I'm calling estimated genetic values that are, well, I'll show you the model, and hopefully that'll make more sense of it. And then we'll calculate those environment and rep corrected genetic values for individuals in the test set with the BLUPs. So the first thing that I do here, this first line here, we're going back to we're using the markers in the test set, and we're multiplying it by the ridge regression marker effects, right? So now this is making predicted values, a vector of predicted values for the 82 individuals that we didn't include in the model when we did the ridge regression. And then this is just subsetting the results from KinBLUP to just the individuals in the test set. I like to use a function called merge to do things like this just because it makes me feel safe. R has this habit, so if you have two vectors that are of identical length, it's quite happy to correlate them with each other for you. Maybe some of you use SAS. SAS does not let you do things like that. SAS forces you to make sure that every individual that you're lining up, for example, is the same individual, but R doesn't care. So you can quite easily get a correlation that doesn't make any sense. It could be negative, it could be 0, because you've just lined your data sets up right. So I like to be really safe about it, and I use this merge function to make sure that I'm going to merge. What I'm going to do is I'm going to merge the the BLUPs that I've made to the phenotype data set. And what it uses is, so you specify first one data set, and that's the the raw phenotypes in the test set. And what I'm doing here is just picking 2 columns from it for simplicity. So the clone variable we need and the raw variable for the trait. So I'm just picking 2 columns out of the raw phenotype data set, and I'm merging to that the BLUPs from gblup. And I'm doing this by clone. So this is specifying a variable that we're going to use to match them. So the variable that matches in the first data set is the clone term, right? That contains the genotype IDs. And then in the second data set that we're merging together, the row names of that matrix are the genotype IDs. So exactly how you go through putting the data sets together to make the correlation is going to really depend on your data set. I'm just giving you one example here. I hope it's not too complicated. But this makes sure that what I now have is a data set that has 423 observations. That's phenotypic observations because there are replicates, probably about 6 replicates per individual in the test set, and 3 variables. So you can see we have clone, CBSD, which is the raw phenotype, and then this V1, it just gives a name to what is the BLUP, the prediction. And so we can do 2 things. We can make a plot. I put a 1-to-1 line for no very particular reason, just to see that there is some relationship here. And then, of course, we want to look at the correlation is typically how we look at accuracy. So this is the correlation, 0.348. Again, I'm hoping everybody's getting the same answer as me. It's the correlation between the prediction and the phenotype in the test set. And that's usually the accuracy that we're interested in. So is everybody on board? Any questions so far? And so this was the prediction from gblup. And this was the correlation with raw phenotypes. I'm going to add more complexity here. Often we use this library LME4. That should also be loaded on your computer. It fits mixed models as well. And we're going to use it to remove from the raw phenotype data set the location and rep effects and just extract values for the clones that are sort of environmentally corrected. So now you'll just have one value for every individual, but we haven't used markers of any kind. And then we're going to use those to calculate the accuracy against. So this function is a good way so you can fit variance components models, for example. There are a lot of reasons that you might use the LME4 package, or specifically this function LMER. It's basic. It's very similar in the way that you use it to, if you've done some basic R, you probably know the built-in function LM that just fits linear models. So you can do analysis of variance with fixed effects, but you can't do mixed effects models with LM. So this allows you to do mixed effects models just without changing that covariance structure, which is what we're doing in like MixSolve and KinBlup. So it has a little bit of a different form, but the formula that we specify is the same. So some of this is just a trust me on this thing. So this formula is going to go like this. We have the variable, the phenotype observation here, the little tilde, and then we have our factors. So what we're doing here is we have a random effect. So this is just how you tell LMER to do a random effect. Okay, so you put it in parentheses, you have a 1, and then this little vertical bar here, and then the value for clone. Then we have fixed effect for location. Notice there's none of this 1 stuff. And then we have, just like, so this is the same format we used in model matrix. So rep %in % location. Rep is nested in location. And then the last part in here is we tell it what data set we're drawing this from. So data equals the raw phenotypic data set, the original one. So you can run this. I can add to this so we can do some things like look at the basic outputs of this model. This might be stuff you might be interested in if you're going to do some statistical analysis in R. You could do model comparisons and some things like that. I'm not really prepared to go into that. But so, for example, we get an estimate of the clonal variance that's explained, again, not using markers, and then the error variance. And then below this are fixed effects estimates and things like that. Yeah? About to do that. In fact, so that is what this next line of code does. So this part is just making it into a matrix, but the real thing is this ranF, so that's for random effects. So that is, so random effects from model 1, there's actually only one random effect in here, but if you have multiple, I just specify $, I want the random effects for the clone. So this is extracting the BLUPs from this model. And again, it's important to realize, so the BLUPs are just the solutions to the random effects, which in this case do not have any covariance. In gblup, we add the relationship matrix for markers. In this case, we just add, it just automatically puts in an identity matrix. So if you look at EGV, I put for estimated genetic value, you have row names that should be the individual IDs, and then you have the BLUPs from this model. And now we have a value that is one value for each individual, and you can use that for calculating accuracy from any given prediction. So what I'm going to do now is subset this EGV, the BLUPs from this from this model to just the test set, and then I'm going to merge them to the predictions that we made using gblup. And I'm not bothering here to compare to the predictions that we made from ridge regression, just because, as you remember, they're identical numbers, so no difference. So if we run these 2 lines of code, we now have a data set that is 81 observations long by 3. So that looks like this. I guess it's kind of destroyed my column names, but it's always going to be in order. So I merged the sort of what's now our phenotypic value, so our value that's been corrected for environmental variance, and this is our BLUP. And so we can make a plot. So you can see the relationship between the predicted value, the GEBV from gblup, and the estimated genetic value from the LMER model on the y-axis here. A little bit of a nicer relationship, and I think that you see that because we've corrected the estimated genetic values for location and rep. And so we can look at the correlation. It makes us appear like we have higher accuracy. I think honestly the most important thing when you're comparing different models and different traits is that you're consistent with how you're calculating your accuracy. So 0.478 is a higher number and it makes me feel better, but it's not actually telling me anything different than correlating to the raw values. So I think that's an important thing to note. I would say that this approach, the correlating to the corrected genotypic values, is probably more common, but there are some even more complex ones that I don't want to touch on here. Any questions? Does that all make sense, pretty much?